Hi, in this video you will learn how to perform a CCA2 attack against a naive padding of RSA. So here is the padding that we're considering. Assume for simplicity that we are working with 10 bits integers and messages are of 5 bits. Okay, so they're strings of zeros and ones of length 5, and then we draw randomness, okay, for the padding over 5 bits, and add a message, and the message and the randomness that we draw. So for each message, we'll draw a random padding, and then it creates the word X, the number X, which is, so we take all the padding on the high order bits, so say R4 2 to the 9 plus R3 2 to the 8 plus R2 times 2 to the 7 plus R1 times 2 to the 6 plus R0 times 2 to the 5. So that's for the high order bits, which are all with the random numbers, R0 to R4, plus the message, then that is mapped to the low order bits of the number that we're looking at. So let's say M4 times 2 to the 4 plus M3 times 2 to the 3 plus M2 times 2 to the 2 plus M1 times 2 plus M0. All right, so that number X then gets raised. So to create the ciphertext, then that number X gets raised to the power E mod N. Okay, so this is an insecure way to do random padding for RSA. And then I'm going to demonstrate here how to mount a CCA2 attack. So an adaptive chosen ciphertext attack that will automatically find always. So the adversary will succeed with probably 1 here. Okay, let's now quickly recap what kind of attack we're talking about. So we assume that we have a challenger here and an adversary. And so our adversary will create an M1 and an M2, two messages that they will send to the challenger, right? And then the challenger will take one of them. Okay, so let's say, MI, and we'll create the ciphertext, which is the encryption of MI. I could be 1 or 2, okay? And then sends it to the adversary. And then the adversary wants to decide if it was M1 or M2 that was encrypted. And they have the right to make decryption queries to the challenger. And so the decryption, the one and only one decryption query that we will do in this attack is the following. So calculate C prime, which is 2 to the E times C mod N, and sends that to the challenger. Okay, so at this point, the challenger has to comply and create an M, which is the decryption of this C prime, and sends it to the adversary. And at this point, the adversary will decide whether or not M1 or M2, whether M1 or M2 were encrypted, okay? So before we get to the actual calculations here, I'll have to look into what is really the goal here of the adversary in multiplying the ciphertext by 2 to the E. So why would we do that? Well, look at what happens here when you remember that C really is an X to the E mod N, right? So if C is X to the E mod N, then 2 to the E times D is 2 to the E times X to the E mod N, which really is 2X to the E mod N, okay? So really, under the exponent, what's happening is, remember that number here that we had created from the message, okay? So number X where there's first the random padding and then bits of the message. Well, that number x is essentially multiplied by 2 here. And so we hope that the message here is highly related to the message M1 or M2 that was encrypted by the challenger. Okay, so what kind of relationship are we hoping for? And there's going to be a little subtlety here. It won't be quite as simple as you would hope, but let's look at the easy case, okay? So what happens when you multiply a number? So remember that number x. What happens when I multiply this number by 2? Okay, what happens to the binary decomposition? Okay, well, instead of here having a, so let me have a highlighter to show you better. So here, instead of having a 9, I'm going to get a 10. And here, instead of having an 8, I'm going to get a 9. Here, instead of having a 7, I'm going to get an 8, and so on and so forth, okay? So what happens is, if the binary decomposition of if the binary decomposition was something along the lines of, and I'm going to start with the high order bits, so let's say R4, R3, R2, I'm just writing the bits here, R1, R0, and then M4, M3, M2, M1. So this is just a sequence of bits that I'm looking at. So this is my number written in binary, where I start with the high order bits. Well, multiplying by 2, okay, what it would give me is a number which starts with a 0 here and has all these bits shifted. Okay, so I'll get R4, R3, R2, R1, R0, M4, M3, M2, M1, M0, and then a 0. Okay, this is the kind of decomposition that this is for sure the decomposition of x. Okay, and now what's going to happen is sometimes, and so if we're lucky and this was actually a 0, okay, that will happen sometimes, well, half the time to be specific. And so when this is 0, then what's going to happen is, in fact, the binary decomposition is just going to be this. Okay, so the number will still fit on a 10, it's still going to be a 10-digit number. Okay, and then during the decryption, what's going to happen is the challenger retrieves then R3, R2, R1, R0, M4, M3, M2, M1, M0, and 0, and then selects, decides that this was the random padding during the decryption process, and this was the message, okay? So then you would hope that the message that is decrypted then is M3, M2, M1, M0, 0, okay? So basically, you take the first 3 digits of the message and then append a 0. So this is highly related. So let's scroll back here. Whoops. So let's scroll back here. And what do we have? So what we would have here is an M that is highly related to whatever message was sent, okay? Because if I take, say, M1, then what I would get in this case is an M which would have at least 4 of the bits of M1 and a 0, okay? So I would very easily recognize M to be the decryption of the C prime that was made out of the encryption of M1, at least if I, as the adversary, if I made sure that I would choose M1 and M2 that don't overlap on those 4 out of 5 bits, okay? And that's the choice of the adversary, so the adversary can do whatever. Okay. Now, there is a subtlety, however, so it won't be always that simple, and it won't always be that simple because that bit here might be a 1. All right, so what happens in this case? Well, here we have, so the kind of the 2 times x before reducing it mod n will be bigger than n, okay? And a number that is bigger than n, then first is reduced mod n, and then we get to choose, take the low order bits and discard the high order bits and making it the decryption, okay? So what happens here is that if you have that R4 is 1, then this will undergo a reduction mod n. Now, because it will be less than 2 times n and more than n, okay, what the modular reduction will look like is that 2x mod n, I'll scroll a little bit. So 2x mod n is simply going to be 2x minus n, okay? That's the only possibility, because on one hand, we had a 2x less than n, then there is nothing happens during the mod reduction. Otherwise, because x is less than n, and 2x is less than 2n, right? And the only thing that happens during the mod reduction is subtracting 1s by n, okay? So what it means is I have to anticipate what would happen to the low order bits. And remember, I don't know the random padding as the adversary, okay? I just know that I know what the low order bits could look like because I have the 2 candidates, M1 and M2, okay? And I don't know what the R's are, but I can just make them up and then do take my mock 2x, okay? So I'm gonna write what the low order bits of 2x can be, and then I'm gonna make things up for the R's, okay, because I cannot know that. And I'm gonna subtract by n, and I'm gonna see what happens to the low order bits, and that's going to be a second candidate, okay? So for what I can anticipate to receive as m prime. So let's scroll back here to my little diagram here. So it means that as the adversary, if I make the hypothesis that M1 was the message that was encrypted, I know that one of the possible M's that I can receive, should the padding be favorable, the R4 being 0, is going to be just a shift of the bits of M1, okay? The 4 out of 5 of the bits plus a 0 in the end. But there is this other case where the R4 was 1, in which case it triggers a non-trivial reduction by n when you have 2x mod n. And then I also know how to calculate the kind of decryption that I would get from that C, okay? So in this case, I have 2 possibilities for M1 and 2 possibilities for M2. And of course, I need to choose M1 and M2 so that that second possibility also doesn't overlap. That would be a shame otherwise, okay? So let's just work it out on an example, okay? So here is our, apologies. So here is our example here. So we have n equals 1073. So of course, conveniently, I'm looking at 10-bit numbers, and E 23, but it doesn't really matter. And then the decryption that we receive is M is 01101, okay? And the 2 messages that were sent originally were the all 0 and the all 1s message, okay? Now, in the favorable case, remember when R4, the padding chosen by the adversary R4 is 0, okay? What I would anticipate is that kind of message in return as the adversary. Okay, but I can see that M, which is 01101, is neither the shift of 0000, which would be just itself 0000, or the shift of 11111, because then it would be 11110. Okay, so I know that I'm already not in this case. So then I have to try to anticipate, for example, let's say I'm taking M2 and I need to anticipate, okay, what happens for M2 if I get a non-trivial modular reduction. So let's try it out with Maple, okay? So, so here with Maple, I'm gonna get the, so I'm gonna copy here the parameters. Okay, so this is n and e. Okay. And then what I do is I'm going to create a possible 2x that will need to be reduced mod n. Okay, so 2x, remember how x was calculated, and it's made of random bits to which I don't have access. Okay, so what do I do here? So 2x would definitely start with the lower order bits 0 and then 1, 1, 1 should M2 be the message that was encrypted, okay? And then I just make up a bunch of high order bits, okay? Because I don't know what they are, and quite frankly, it doesn't matter because subtracting by n is only going to affect the lower order bits of that number, okay? So whatever happens to the higher order bits is going to be wrong, unless that was extremely lucky, but that's okay, because during the decryption process, these high order bits get dropped because this is the random padding, only the message is kept. So here is my mock 2x. This is a number, by the way. And then I'm gonna reduce it mod n, which really means in this case that reduction mod n that we're talking about is simply a subtraction by n. And here, and I'm gonna look at the binary decomposition of it. Boom. And so here is what we got. Okay. This is my lower order bits. Everything else would be dropped, you know, during the decryption process, right? Because these are the random padding bits. And then the lower order bits would be kept and returned as the message. And here we go. We have a 01101, which is the decryption received. Okay. So what that means is I conclude that M2 was the message that was sent, that was encrypted by the challenger and sent to the adversary. And so the adversary that follows that recipe would win the game all the time, right? For a good choice of M1 and M2, of course. So for when you're the adversary, typically in a question, I will give the public parameters, of course, but also the M1 and M2 chosen by the adversary. Like if you were going to do it yourself, you'd have to make sure that M1 and M2 do not overlap once you apply the kind of transformations that you anticipate when you receive the answer from the challenger, okay? So here I know, and I win. So now you know it was a little complicated, a little convoluted, but not very complicated. And now you know how to perform a CCA2 attack against a naive padding of the RSA cryptosystem. Thank you for listening.